Guys, I have some videos from later in the course, but none that cover the beginning material. Okay, so today what we're going to talk about is quadric surfaces and conic sections and ways of visualizing those things. You can see the ghost of a hyperbolic paraboloid here, so we'll get there. The basic idea is that if I have surfaces, functions that are surfaces, those are very difficult to visualize. And in a lot of fields, you never work with a three-dimensional plot. Is there a desk back there? Yeah. All right. You don't work with three-dimensional plots. You work with contour plots or level curve portraits, which is what I'm going to be talking about today. Okay. So we're going to sort of guide our discussion with an example this morning. We're going to look at the function I introduced last time, z is equal to x squared minus y squared. And our analysis of that function is going to lead us through the content that I want to discuss. And then we'll look at some more examples after we have the basic tool set built out. So this is a type of function called a quadric surface, which I will define later. In particular, it's called a hyperbolic paraboloid. That is not something that I care if you know. If you're interested in learning classifying the types of quadric surfaces, you can do that in chapter 12.6, which we're mostly skipping. It has a graph that looks like this. So it bends this way, and then down, and then looks like this. Sort of a saddle, I think, is the shape I described this as last time. The reason it's called a hyperbolic paraboloid is because if you cut it in this direction, the cross sections look like hyperbolas. So if you put that on a flat graph, it would look like this. And if you cut it in the other direction, sort of top to bottom, in this direction, you get parabolas. So hyperbolic paraboloid. So it does look like this if you look at a flat picture. So I'm going to show you how I came up with this picture, and we're going to do an analysis of this based on these sorts of ideas of cutting a surface into pieces and analyzing it that way. So what we're going to do is we're going to use an idea called level curves to look at this. So level curves are a way of decomposing the behavior of a surface into pieces that we can understand in a flat picture. Topographic map. In other fields, you might see these things, I think I mentioned last time, equipotentials or isotherms or isobars, places where some physical quantity is held constant. So the definition of a level curve is a level curve of a function f of xy is the set of points xy. So this is in the plane. It's not a three-dimensional picture in this case. It's a two-dimensional picture. It's the set of points xy that satisfy f of xy is equal to k for a constant k. It's all of the inputs that produce a specified output. So in our example, I can produce some level curves by choosing some values of z, choosing some heights, and then seeing which points x and y produce those values. So if I pick height is equal to 0, that gets me the equation 0 is equal to x squared minus y squared. If I picked z is equal to 1, I get the equation 1 is equal to x squared minus y squared. If I pick z is equal to minus 1, I get minus 1 is equal to x squared minus y squared, which for reasons that will become apparent, I'm going to rewrite as 1 is equal to y squared minus x squared. So whatever these are, the solutions to these, the solutions to this equation are all the points that produce height 0. The solutions to this equation produce height 1. The solutions to this equation produce height -1. And if we can plot those things, we can get a picture of what the surface is doing. Of course, that means we have to be able to plot these things. And from querying the class last quarter and the beginning of this one, my understanding is that quick methods for plotting conic sections was not always a standard topic covered in your earlier courses. So these are examples of a type of function called a conic section. And so I'm going to go through methods for plotting these, like the standard conic section plots, so that when we're doing a level curve decomposition, you can actually do what you're supposed to be doing here. Right? This is kind of a part of the standard tool set. Okay, so first off, just in case and for sort of culture reasons, conic section means cut a cone. So the ancient mathematicians define these things sort of naturally geometrically by taking a cone and then slicing through it with a plane. So if you take a cone and you slice it through a plane straight across, you get a circle. So you cut through the cone and you look at the incision that was left behind, the figure you get as a circle. And as you cut in different places, you get circles of different radii. If instead you had decided to tilt your plane slightly, you wouldn't get a circle, you would get this figure, which is an ellipse. If you had cut the cone straight up and down, parallel to the axis of the cone, say, you would get a figure that looks like this. Oops. So same cut on this side looks like that. That's a hyperbola. Two branches because you're cutting through both halves of the cone. And then there's the degenerate cases, the non-bendy stuff. If you cut through the exact middle of the cone, you get a point. And there's one more, which I will just tell you is a line. How do you cut the cone to get a line?
Cut diagonally?
Cut, yeah, exactly along the surface of the cone, right? You set up your plane so that you're sort of riding the edge of the cone, and you get a line. So those are your sort of standard basic conic sections. So one of the things that Descartes did when he turned geometry into analytic geometry was he took these sort of intuitive sort of space ideas of what these figures were and then turned them into equations. So the analytic geometry of all these, form of all these looks like this. So an ellipse has the form x squared over a squared plus y squared over b squared is equal to 1. I'm centering all of these at the origin, so these are non-shifted and non-rotated conic sections. Hyperbola comes in two forms, x squared over a squared minus y squared over b squared is equal to 1, or y squared over b squared minus x squared over a squared is equal to 1. If you've done this before with things like focal length and like the c value and all these triangles, I'm not doing any of that. I just want you to be able to draw quick sketches of these. I should point out here circles are ellipses because x squared plus y squared is equal to r squared can be rewritten as x squared over r squared plus y squared over r squared is equal to 1. So a circle is an ellipse where the a and b values are the same. And then the version of parabola that we need is y is equal to kx squared or yx is equal to ky squared. And all the other conic sections can be derived from these basic forms, usually by use of completing the square. So there's a deep dive into this stuff in section 10.4. I really just care that you know the basic shapes and how to plot them so that we can produce things like level curve plots of surfaces. All right, so how do you plot these? So I'm going to start with the ellipse because the method for the ellipse is the same as the method for the hyperbola. X squared over a squared plus y squared over b squared is equal to 1. A is sort of like the x radius of your ellipse, and b is sort of like the y radius. So what that's in the same way that like the circle has the same radius for both x and y, which is why it's a circle. So the way that you plot an ellipse is you start at the center of the ellipse. In our case, everything is centered at the origin. You move a units in the x direction because that's your x radius, and b units in the y direction because that's your y radius. And then you draw a rectangle. And then the ellipse is the figure that touches all four sides of their midpoints. The fastest way to draw an ellipse is with this rectangle method, I think. I mean, you could do it without the rectangle. I'm doing the rectangle because a hyperbola is basically an ellipse that's been flipped inside out. Okay? Fastest way to do it. Those of you that have done this in the past may remember all kinds of things about A and B switching places, and sometimes A is on the X and sometimes A is on the Y. I don't do any of that. X goes with A and Y goes with B. To draw a hyperbola, first it's nice to recognize that you're looking at a hyperbola. I know that's an ellipse because there's two quadratic terms and they're both the same sign. If I'm looking at a hyperbola, I have two quadratic terms and their signs differ. I'm going to draw the same exact rectangle. I have an A radius, or an X radius A, and a Y radius B. I'm going to draw a rectangle containing the ends of those things. Now hyperbolas have a little bit more structure than ellipses do. So hyperbolas are actually asymptotic in the sense that, and this doesn't usually come through in the graphs that we make, hyperbolas always sit between two crossed lines, and they're asymptotic to those lines. Okay, so as you go towards infinity, they start looking linear. And the asymptotes turn out to be the diagonals of the rectangle. Do I care about writing down what the equations for the slopes of those are? No. I just know that I want you to be able to sketch these things. And just like with an ellipse, if you want, you can label the four possible vertex points. And this is what I mean about an ellipse is sort of, or hyperbola is sort of like an ellipse that's been turned inside out. I know that it's got branches. You can either memorize this or you can derive it. I just derive it. It's either opening left and right or up and down. And without memorizing, you can just tell by plugging in the two possibilities for the vertices. Either y is equal to 0 or x is equal to 0. And only one of those will work for a given equation for a hyperbola. If you put in x is equal to 0 and you ask for the y values that correspond to that, you will get the equation minus y squared over b squared is equal to 1, which will give you y squared is equal to minus b squared, and that's impossible. Can't take a square root of a negative number in this setting. So that means the vertices that have x is equal to 0 are not on the hyperbola because they're not solutions to the equation. This point and this point can't be used, which means the hyperbola looks like this. You don't need to draw all this stuff when you're doing it yourself, but this is internally, if you've not done this before, this is the fastest way to come up with a sketch of a hyperbola in standard form. If instead you have y squared minus x squared, you would have exactly the same picture. But when you solve the equation, you would put in y is equal to 0 and get an impossible equation. So let's actually do a slightly more complicated one here as an example. In fact, if I gave you a shifted one, x minus 1 squared over 1 squared minus, let's put y here, x squared over 2 squared is equal to 1. That's a hyperbola because we still have two quadratic terms. They have opposite signs. Whatever is happening here, my sort of x radius a is equal to 2 and my y radius b is equal to 1. But now I've got a shift where the center of the box isn't at 0, 0, it's at 0, 1. That's what the negative 1 attached to the y does. So this has a shifted center. 0, 1. From that point, everything else is identical. The center of the box is at 0, 1. I'm going to move 1 unit up and down in the y direction because that's the y radius, and 2 units left and right in the x direction because that's the x radius. So I get this rectangle. I put asymptotes on it. And now I can check, are the vertices here and here or here and here? Actually, like, I mean, obviously, since I got it one way over here, it must be the other way over here. The way to check that would be to say, well, maybe you think that it's these two, and those two are going to happen when x is equal to 0. So when x is equal to 0, you get the equation y minus 1 squared over 1 squared is equal to 1. And that is a solvable equation because I can take a square root of a positive number. So this must be opening up and down. And that's all you need to be able to do with these things. I presume we can plot parabolas at this point in our lives. It's probably the thing you've learned the most, other than plotting lines. So these are the sort of basic shapes that show up when we're dealing with quadric surfaces. Ellipses, circles, lines, hyperbolas. All right, questions about, I know, like I said, there's some Chapter 10.4, which is the conic sections chapter. I think this is generally not covered by many professors. Do not do 10.4 when they're doing Calculus 2. There's a lot more you can say about this. There's things like the focus and the directrix and all kinds of structural things you can say about these. But all we need to be able to do is produce quick graphs. And this is good enough. All right, questions about this before we go on to actually using it? Yep.
Yeah, are there any like faster strategies to do this other than solving equations when x is equal to 0?
You can just memorize that if the x squared is positive, it's left and right, and if y squared is positive, it's up and down.
Oh, okay.
Yeah, I'm trying to give you a trapdoor method if you don't remember. Right? If you don't remember if it opens left and right or up and down, like if you memorize it, just do that. You can do whatever cut down version of this you wanted to. Like if I was working quickly and I wrote x squared minus y squared is equal to 1, I would just like say, okay, well there's the box, and then there's these guys, and since x squared is positive, it looks like that. I wouldn't write down any other numbers. I just sketch the graph, right? So whatever version of this is supposed to be all the support work you need to build this thing, and you can use whichever amount of that you want. Many people have never seen this before in this class for some reason. And so I'm trying to give like the whole tool set. If you like this kind of analytic geometry, you can actually take an entire class on it. All right, so let's use this tool set to go back to the surface that we started with. All right, so we began the class by looking at z is equal to x squared minus y squared. And we were going to approach this thing by trying to understand its level curves. That is a flat picture that does not involve the three-dimensionality. I squeeze it down so I can understand it. And if I wrote down z is equal to 0, I got the equation x squared plus y squared is equal to 0. We dealt with this one yesterday. So this factors as x minus y times x plus y is equal to 0. So either y is equal to x or y is equal to minus x. So what this means is every possible value where that function produces height 0 is captured by these two lines. So I'm going to draw that in a portrait. This is sometimes called a contour map, a topographic map. So this, try to use different colors here. This is the set at which this function has height 0. So we continue. Where is it height 1? Well, when 1 is equal to x squared minus y squared. And if I want to be pedantic, I could write this as 1 is equal to x squared over 1 squared minus y squared over 1 squared to really emphasize that I'm looking at a hyperbola. It's a hyperbola that has x radius 1 and y radius 1, and it opens left and right. 1, 1, 1, 1, draw the box. Oh, it's convenient that the lines I drew are the asymptotes, so I don't have to do any more work for that. And so this curve, that's where z is equal to 1. And this is where z is equal to 1. We can continue. I'll do one more on the positive part before we flip. I'm going to choose z is equal to 4 as my next value. It's often worth spending some time thinking about what good values are for producing a level curve portrait to make the math easy. Because if z was equal to 4, you're looking at 4 is equal to x squared minus y squared, which is the same as 1 is equal to x squared over 2 squared minus y squared over 2 squared. Half the battle is just putting these things in standard form. So, same hyperbola, but now the box has x radius 2 and y radius 2. 2, 2, 2, 2. Z is equal to 4. Z is equal to 4. Already we can tell some structural things about what's happening here. So one question that gets used, one way that these plots get used in fields that are not just visualizing things in your calculus class, but if somebody put that in front of you and told you those are lines of constant temperature, and then they ask, where's the where are there regions where the temperature is increasing more quickly than other regions? So, for example, if that is temperature 0, and this is temperature 1, and this is temperature 4, the distances that it takes to do that increase are pretty far apart from each other relative to up here or down here where these curves are all smashed together. So from this picture, you can read over here, stuff is happening really quickly. These contour lines are bunched up, which means things are changing fast. You can also read off, well, if this is 0 and this is 1 and this is 4, it kind of looks like the function starts small and gets to 1, but then it increases to get to 4. So it's bending up in this direction as well. It bends up as it goes from here to here. It also bends up as it goes from here to here, but faster. It also bends up as it goes from here to here, but even faster, right? So the further away from the center you get, the faster that function is headed up. So we should take a look at some of the negative heights as well, because we've left off two big regions of the graph here. If I look at z is equal to minus 1, I get minus 1 is equal to x squared minus y squared, which is the same as 1 is equal to y squared minus x squared. That's also a hyperbola with the same box that this one has, but it opens in the opposite direction. So 1 is equal to y squared over 1 squared minus x squared over 1 squared, and it opens up and down, which means it looks like this. That's z is equal to minus 1. And if you do the same thing for z is equal to minus 4, you get 4 is equal to y squared minus x squared, which is the same as 1 is y squared over 2 squared minus x squared over 2 squared. That is to say, we're looking at, okay, oh, that's terrible green. Ah. You wonder why they make chalk in these colors sometimes. Oh, now I've disparaged Higueromo. I can't post this video online. Okay, so oftentimes when you're presented with a picture of a function, this is a more useful way of understanding what's happening than the actual three-dimensional plot. Three-dimensional plots are sort of hard to manipulate. You have to rotate them to see what's happening. In practice, many times when you're working in function setup this way, this is what you get to deal with it. And from it, you are supposed to extract the behavior. So when I look at this, I think, okay, there's a flat point right here. The function is increasing in height as we go this way. And it's not just increasing, it's increasing the speed with which it's increasing. So it's bending up and out at you as you go this way. So it's sort of U-ing out on the board in this direction. In the other direction, as you go this way, the heights go from 0 to -1 to -4, which means it's bending down in that direction. So down into the board and up out at you. So now I'm going to try to draw the hyperboloid, and just to sort of anchor this, I'll show you where those curves sit. Trying to drop any of these chalks while I do it. All right, so let's look at a hyperbolic paraboloid that I drew earlier. So this, and this, and this, and then there's this guy down here. And then this bends in, and comes down this way. All right, so the curves that I've drawn here on the corresponding surface look like this. So the green curve is right here. That's the curve at the bottom. And then as we slide towards the center, we get to the yellow curve, which is at height 1. So that looks like this. And then on the back side, it looks like this. The blue lines are sort of interesting because the blue lines suggest that the lines that go through that saddle point are actually straight lines. So if you actually drew all of the lines with height 0, you just get a flat straight line that goes through and then back out the other side, and a line that comes in from the back side and goes like this. So the hyperboloid has this x that actually determines it in the plane. As you go up the other direction, you get the orange curve, which looks like this. Oops, I should dash that. And here. And then the top curve is the red one. So essentially what the level curve portrait does, this level curve picture, is it lets you take the complicated three-dimensional surface and sort of cut it into pieces that let you understand what's happening. I find this harder to visualize in a lot, especially with more complicated functions, than this. I will point out that if you have not seen these terms so far, other names that you might have for these, if you're studying electricity, these are often called equipotentials. If you're studying heat, they are called isotherms. If you're studying topography, these are the lines of constant altitude. So you imagine if you look at a topographic map, this is what you're looking at. They're called isobars in the study of pressure. I don't know what the name is for lines of constant concentration, but it's another sort of thing that comes up in various chemistry applications. But these pictures tend to be what you get. Now you might wonder, why spend all this time on this sort of baby example here? And the answer is that these guys are a part of a class of functions called, like I said earlier, quadric surfaces. So let me define for you what a quadric surface is, and I'll try to justify why we would care about something so simple. You think about surfaces must come in all kinds of flavors that don't look like this. They must be like sort of wildly oscillating and bumps everywhere and maxes and mins. So the picture there is, first off, let me tell you what a quadric surface is. Quadric surface. So quadric surfaces are covered in chapter 12.6 in exhaustive detail. I told you earlier I don't care if you can classify these things, I just want you to be able to do portraits like this of them. So a quadric surface is a surface of the form z is equal to ax squared plus bxy plus cy squared plus dx plus ey plus f. Generally a surface that's generated by a two-variable quadratic polynomial. The one we just looked at over there, z is equal to x squared minus y squared, is a quadric surface because it has a is equal to 1, and c is equal to minus 1, and b, d, e, and f all equal to 0. And they come in some really important basic flavors. There was the parabolic or hyperbolic paraboloid, hyperbolic paraboloid. These are important because they have saddle points, points where they bend down in one direction and up in the other. There's also just paraboloids. These are important because they have maxes and mins. They bend all the same direction at a max and min. All up or all down. And the point of quadric surfaces is that every other surface, when we're studying the behavior of how a surface works, these are enough to capture the behavior of general surfaces. General surfaces will have points where they look like hyperbolic paraboloids, saddle-y type behavior, or points where they're all bending in the same direction. That's related to our study of maxes and mins later. And to give you an idea of why we care about that, in one variable, when we wrote down the graph of a function, we talked about, and you have spent lots of your life thinking about tangent lines. This is also called a first order approximation. It's linear. You're replacing the function with a linear function that acts like it. Then we did Taylor series, which I know is everybody's favorite topic. We did Taylor series, and Taylor series introduced the idea of n-variable approximations for a function. That's what a Taylor polynomial was. In several variables, the best one to work with is to just restrict our attention to approximating parabolas. Second order approximation. Second order approximations, that is, parabolic approximations, tell us not just the tangent line to the curve, because the parabola and the tangent line have the same slope at that point, but they also tell us something about how that curve is bending at that point. There's a measure of concavity attached to a quadratic approximation for a function. Does it bend up or does it bend down? If you guys remember the second derivative test, that's what the second derivative test tells you. Second derivative positive means the approximating parabola is upward opening. Second derivative negative tells you that the approximating parabola opens downward at that point. These two surfaces, the hyperbolic paraboloid and the paraboloid, play the role of the parabola when we're approximating surfaces instead of curves. So the reason we're spending time on this is when we get into the deeper material, we're going to be using these basic figures to deal with general surfaces. All right. No. All that. I dropped one. Okay. So before we go on to, I'm going to do a couple more examples of some surfaces to think about and another contour plot where we're just going to interpret what's happening from a contour plot. Any questions about anything I've done so far? I can answer here. Cool. All right. So let's look at something like, what if I gave you the function y is equal, sorry, that's even better. F of xy is equal to the square root of x. And I want you to draw a level curve plot. Yeah, pick me some values of z to use here. I can give you a really good one. What you want?
1.
1. Okay, that's a good one. So 1 is equal to the square root of x. You square both sides, and you get 1 is equal to x. So now you go over here to your level curve portrait. And I got to draw something. What do I draw?
Vertical line.
Vertical line. The vertical line x equals 1. Don't get tricked here. This is a function of two variables, even if the y is not present in the formula, right? So this is some point. It's x is equal to 1 and every single possible value of y. So this line right here is the line where we are constantly equal to 1 in temperature or altitude or whatever you want to measure with this. Height. Other values?
4.
4. Oh, okay. You sure? Z is equal to 4 gets us 4 is equal to the square root of x, and so 16 is equal to x. Okay, so let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so way out here is z is equal to 4. I'm going to pick a couple more for you. Z equals 2 will give us a line where x is equal to 4. I did exactly the same thing in the last class, which is why I did that. So 1, 2, 3, 4 is z is equal to 2. And then there'll also be a line at 9. 5, 6, 7, 8, 9. Z is equal to 3. And from there, I can't believe we left off z equals 0. And that's all you need. I mean, just even a couple of these, I think, would have been enough to understand what this plot is doing. So, tell me what this plot is doing. Somebody, go ahead, interpret that for me. What does it look like? Johnny?
It's continually going up, but gradually less and less each time.
Okay, so that you can get off from the fact that you got 1 unit to 1, and 3 units, 4 units to 2, 5 more units to 3, and 9 more units to 4, and so on, right? So the spacing is getting wider. So from the side, if you looked at it, it would look like a square root function, right? You can read off those dots right there are dots on a square root function. What else? So that's good. It is. It's sort of like definitely like increasing but decreasing the speed at which that's happening. Yep.
It extends infinitely in the y direction.
It does. Okay. Well, yeah. Yes.
With negative z values, it's flipped.
Is it defined for negative z values? Let's actually check that real fast, because I didn't write any negative values down. If z is equal to -1, then -1 is equal to the square root of x. Is root x possible? Can root x produce -1 as an answer? X is equal to I? So I guess it flips in the sense it goes into the complex plane somehow, but yeah, no. So this is actually not defined in real numbers because the principal branch of the square root can't produce negative numbers. So it's actually just nothing over here. But well observed that we needed to look at that, right? That I left that out. What else? So you mentioned that it extends infinitely in the y direction. can you tell me something about like, now just, you got to be like, put yourself in math professor mode and just wave your hands around. Show me with your hands what it does. Okay, I see a lot of arms going like this, right? So yeah, it's hard. You don't have infinitely long arms, but the idea is it's almost like a wave or something, right? It's a flat line here, and then it's a sheet that sort of curls up like this forever. This probably is and this is an example of, these are very fast to produce and easy to get a lot of information out of in a way that you'd have to really work at with a three-dimensional rendering to get the same information. In fact, when you look at something like this, the idea that, like Johnny said, the idea that you can go along a line like this and see the way that it's curving, you can just read off these things. Any strip that you pull is going to have an associated cross-section, like you tipped it up and you're looking down the side of it. It's a profile of it. In fact, this is called a trace. When you rotate it into another direction and look down the sides. Okay, so we have one more idea here before I cut you loose today, which is a lot of times when you put a function in to a plotter, or you look in a scientific paper, you may not get a three-dimensional picture at all, or even a defining function. So I'm going to try to draw one of these, and I want you to think about it and tell me what it is I'm drawing here. It's okay. So let's see if I can do this. So I have, maybe I'll put z is equal to 20. Maybe over here I will have z is equal to 20. And then there'll be a ring here. Z is equal to 10. Here z is 10. And then z is 0. And there's some line out here where z is equal to 0. So 20, 10, 0. I better pass through 10 again if I'm going to get back up there. So z is 10. This is a typical sort of plot that you see in all kinds of applications and papers. There'll just be some kind of contour plot that looks like this. And you have to interpret, what am I looking at here? You're out in the mountains somewhere, like, your plane crashed and you're out in the mountains and your phone broke when that happened. There you are in the wilderness and all you have is your trusty paper map. What am I looking at? What does it do?
Well, that one there's like a hole.
This guy right here?
Yeah.
A hole?
Well, like a kind of. I don't know how to. It's like a bowl.
Yeah, the last class,
Like a hole.
the last class
Like a
kept
hole.
saying it's like a volcano.
It's like a volcano. But the other one's more like a volcano. It goes up.
Well, so you're right. There's definitely a bowl here because you go from height 20 down to height 0, right? So it definitely has a little cup. But that cup has a ridge on the outside of it, right? There's this height 20 ridge on the outside, and then what happens when you get off of that height 20 ridge?
It goes
You
back.
start going down again. So this is why they call it, like, the idea of like volcano is this goes up to a ridge and then it sinks down again to the sort of bottom of the crater. So if you looked at this from the side, what this bit would look like is presumably your height is, we don't actually know, the height here is between 10 and 20. So you're something like, you go up to this lip at height 20, and then you dip all the way down to 0, and then you come back up again to 20, and then you start falling back down again because you go back through height 10 to height 0. So what I'm imagining here is I'm traveling through the graph along this line. So I'm increasing in height until I get to 20. I fall down to height 10, and then height 0, and then I'm back up through height 10, back up to height 20, and then I start falling back down again to 10. Then what? The other part's pretty easy. There's no volcanoes there. Like cone, right? It goes up and down again. So as you keep traversing this thing, you go up and then down. This ability to interpret these things, this is sort of like the real skill here. Computers are very fast at producing these contour plots, but the interpretation of those contour plots is up to you. Right? So the real skill is not in producing these, although you'll be practicing those in the homework as well, but in interpreting what it is that you see when you get one. And I said, so you start flipping through scientific papers in any field, And with a surprising amount of regularity, you fall across things like this. Sure, it'd be nice if we had more lines, right? So we can say more. No, not more lines. Because like the more lines you have, the more information you've got about how quickly things are increasing or decreasing in height. Okay, here's another question. This is a question related to an idea we're going to learn in just a little bit. If I was on the side of this mountain and I was tired and I didn't want to go up or go down, what direction? Say I'm at this point right here, and I'm really tired. What direction should I go? Along the curve, right? Because I'm not going to climb up or down. So that's going to turn out to be tangent to the curve, right? There's going to be a tangent. If you guys remember your vector stuff at the end of 143, if I could parameterize this curve, I could take its derivative and it would tell me how to move in that direction. Oh, look, that's going to be the direction that my height doesn't change. What if I wanted to get down the mountain as fast as possible? What direction should I move? Normal to the curve. This way. Perpendicular to the tangent vector. So this guy right here, so if I go normal to this curve, I get the direction of steepest descent. And that's called the gradient, if you've seen that in context before. So geometrically, the gradient vector, if you've seen that before, or you've seen that word show up in other contexts, is the normal, this is the magic of the gradient. The direction at which you can increase or decrease the fastest is perpendicular to the curve of constant height that you're on. That's like a magic piece of geometry. And that is part of what we're going to be studying as we go into the later parts of this chapter. How we actually do, from this level curve picture, how we can use it to analyze the behavior of the surface in terms of steepest decrease, steepest increase, and the directions in which we can keep our height constant. That's a fundamental geometric relationship there. All right, that's enough for you to tackle all the stuff from 14.1. And then the 12.6 stuff I leave to you to do because that's all the quadratic surfaces, level curve things. Are there any questions before I cut you loose? All right. So Dr. Champney is going to be here on Thursday and Friday, and she'll be discussing partial derivatives, which is 14.3 is what she's going to do on Thursday. And then on on Friday, I want to do the usual lab day workshop stuff. So I'll have a worksheet for that. And I will see you guys on Monday. I'm sorry I won't be here. This is an inconveniently timed conference. So